Okay, Assalamu alaikum everyone, and welcome to another session for Triple E 6311. So in today's class, what we are going to discuss is basically a topic which is a little different than what we discussed earlier in the previous few of our earlier classes. So till now what we have seen is basically we have talked about the economic load dispatch problem, so ELD problem, for all thermal system. So that means in the power system or the power station under consideration, we talked about only the type of generators or generating units where all of the units were thermal type. Okay, so all of the units were actually expressed. The costs of the units were expressed by some function of this form, alpha plus beta PGI plus gamma PGI squared. So some sort of quadratic function where this f was of course the function of some individual generating units. However, all the units under consideration was thermal. Okay. So the fitness or the objective in those cases were basically to minimize the total cost. Okay, so if there are n number of units, so we were talking about, let's say, that our target would be to minimize the cost for all of the units under consideration. So if there are n units, so you can say the f total is basically nothing but summation of fi, where I is 1 up to n. So this was the discussion that we took earlier. And then basically what we did, we applied the Lagrange multiplier method uh, for equality constraint, and for the inequality constraint we introduced the concept of the KKT conditions. So this was the case for all thermal system economic load dispatch problem. So now what we will do, we will actually shift our focus a little bit to a new thing, a different thing, which is known as hydrothermal coordination. So in this case, our target would be simply, again, we will be trying to minimize some objective function. So we will be having some objective function. We'll come to that later on. So again, this is the generalized form. So our target would be again to minimize some objective function. And of course, this objective function should be represented in terms of some cost functions. And of course, subject to some constraints. So there could be some equality constraints in general, as well as there could be some inequality constraints. And like before, if we only have to deal with equality constraint, we will be applying the Lagrange multiplier alone. However, if we have both the equality constraint as well as the inequality constraint, then we have to take the help of the Lagrangian as well as the KKT conditions. So this would be the case. Okay. So now let's try to focus on the problem at our hand. What is basically meant by the hydrothermal coordination? So the difference between the hydrothermal case and the previous case, the all thermal case, lies in the fact that, let's say, for example, for any country or any region, you have both the resources of thermal units. So let's say this is my thermal units. This will of course generate some power. So the input to this unit is basically coming from some thermal concept, and this is actually connected, let's say, to a common bus. This bus is supplying some common load, and here of course you have hydro units. And the hydro unit basically runs with the help of some hydropower, which is probably coming from, let's say, some storage tank. So there is some inflow of water. This is my reservoir. Of course, this is a much simplified diagram. This is the generating unit. And this is the injection of power to the common bus. Ultimately, both are combined, both are supplying the load in a combined manner. So the main difference lies in the fact that the thermal unit as well as the hydro unit here, both are responsible for supplying a common load. This is of course different than the case where we have all thermal cases. Now, if we try to formulate this kind of problem, okay, we have the thermal units as well as the hydro turbine units or hydropower generation units to supply a common load. Then if we try to look into the associated costs for each of the units separately, so the thermal, as we know that, of course, we are talking about the running cost or the operating cost. So the main cost lies with the fuel, okay, cost of the fuel. So for the thermal units, you have to buy the fuel, you have to store the fuel, you have to burn the fuel, and then you have to generate the steam to run the steam turbine, and then you generate the power, electric output. What about the hydro? Hydro, how much fuel cost is associated? Actually, there is no fuel cost associated. So this is the interesting part. So in case of hydro, you don't have to bother about the fuel cost. Okay, so it is free of cost. The fuel basically is water. So basically you have inflow of water, and we don't bother about the fuel cost here. So when we talk about the hydrothermal coordination, if we try to formulate the problem in terms of this optimization function, in terms of some optimization problem, if our target remains the same, like if we say that, well, we still want to minimize some cost function, and even in the presence of hydro, we have the fuel cost associated with the thermal and no fuel cost associated with the hydro unit. So the total cost for the fuel actually is associated only with the thermal units. Okay, so this is only associated with the thermal units. So our main objective function is more or less the same as the all thermal cases. Okay, remember, this is again the economic load dispatch problem in general, but for the case where we have some thermal units, thermal generating units, and some hydro generating units. So this is still, we are under the topic of ELD, economic load dispatch, but now the generating stations have different features, some hydro and some thermal. Hydro, they don't have any fuel cost. Thermal, they have some fuel cost. So if I try to formulate the optimization function for this, or the objective function for this problem, I again have to take help of the fuel cost associated only with thermal units. So my target would be again to minimize the fuel cost associated with thermal units. But now we can clearly see that if I can use, or I can share some power from this thermal where the fuel cost is associated, if I can share, let's say 50% of the power, for example, 50% of the power is shared by hydro, so I can automatically reduce the fuel cost by a margin of at least 50%. So in this manner, we can easily say that, well, with the introduction of hydro, of course, we are ignoring all the capital cost. Remember, we are only considering the running cost or the operating cost. In practice, the hydro units, the construction and installation of the hydro units, they will incur higher cost, higher capital cost compared to their thermal counterpart. So as I said earlier, again, I repeat, so we are only considering the running cost, like the fuel cost for the thermal units and whatever running cost is associated with the hydro units, because no fuel is associated there, so fuel cost would be zero. So from that point of view, if we can reduce the thermal contribution for satisfying a common load, with the introduction of the hydro generation, then automatically my fuel cost will become less and this function value will become less. So till now what we have discussed is all about, let's say, the benefits or the plus points of hydro. What are the associated drawbacks, or is there any constraints that we might need to consider with the introduction of hydro? Yes, there is. So the problem with the hydro is that you have to become dependent on the nature. Okay, you have to become dependent on the nature, because the reservoir, the inflow of water that is coming, basically it varies throughout the year. So the inflow of water is not constant, is varying, and it varies, let's say, throughout a year. Luckily, we don't have to go beyond a year, because generally this flow of water or the inflow of water, depending on whether it is a rainy season or a dry season, okay, if we divide the whole year into, let's say, some rainy season and some dry season, so this variation of water, inflow of water, or the reservoir head, so this head or this reservoir level, the height of the reservoir, water reservoir, height of the water inside the reservoir, this actually varies throughout a year in a cyclic manner. This is the plus point for us. So that will vary in a cyclic manner. Means after 1 year, the cycle will be repeated. That means in a year, probably you will get few months for rainy season and few months for the dry season. So in the next year, let's say in 2021, there was a rainy season. In 2021, there was a dry season as well. In the 2022, more or less, you expect that, well, you will get another rainy season as well as you will get another dry season. So the season wise, this is cyclic in nature. So the reservoir level, there is the height of the water level within the reservoir, will actually vary in a cyclic manner depending on the season you are following. So in the coordination case, what we can do, let's say whenever our water level or water head in the reservoir is high, okay, the water head is high. So when the head is high, that means you have more potential energy, where head is basically h, the height of the water in the reservoir. M is the mass of the water, g is basically the gravitational force. So if mgh is high, you have higher potential energy. So that means that higher potential energy can easily be converted into high kinetic energy, and that high kinetic energy will be converted into that is the rotational energy that will run the turbine, and the turbine will run the generator, and ultimately you will get the electrical output. So the electrical energy output. So that means there is a direct linkage between the head height available here in the rainy season. Higher head means higher electrical output from this hydro unit. In the dry season, during the dry season, so what you will do, you will get less head height. So H will become less, kinetic energy will become less, and the electrical energy available or possible output of electrical energy from the hydro units will become less. So what you will do in the rainy season, because you have higher amount of contribution from the hydro possible, so during the rainy season, what we can do, we can choose, let's say, this is my rainy season, this is my dry season, and if we divide into, let's say, some base station, base and peak, base power station and peak power station, probably you are already familiar with this. Base means basically the unit will run with a constant output, more or less a constant output. Okay, so let's say if this is the load variation, something like this is the minimum load, so probably around here you will run your base load. So this is your base load value, and the remaining peaks will be supplied whenever there will be peak. The peak will be supplied by the peak generating unit. So the base load in the rainy season, because you have the hydro unit availability is higher, so you run the hydro units as your base units, and the peak unit as the peak generating units, you will use the thermal. On the other hand, during the dry season, you go for the reverse case because you have less hydro, so you reserve it for the peak operation, and the thermal unit you run it as the base unit. So the fuel cost automatically in the dry season, you can expect the higher fuel cost, whereas in the rainy season you can automatically expect that as you are running the hydro unit as your base station, so the fuel cost will be less. So in this manner you can have some coordination between the hydro units and the thermal units. So all these are basically some theoretical basics that I introduced you with. So now we will slowly go into the mathematical part. That means we'll be going into the formulation of the objective function, how we are going to deal with this in coordination, hydrothermal coordination mathematically as an optimization problem, of course. So as I said earlier, probably I lose the track from there on. So the hydro unit, there are some constraints. Okay, I was talking about some constraints, so I probably missed the point earlier. So let me go to that point. So hydro has some constraints, means you can only use that amount of water which is available to you, of course. Okay, you are not buying actually fuel, and you are not storing the fuel as you did with the thermal units. In the hydro, you can only play with the available head depending on your season. So there is a constraint associated with the hydro, that how much water is available to you at a certain instant of time. Okay, and this instant of time is generally taken into hours. Okay, so the duration, the hydrothermal coordination, we usually we use, or usually you go for hours. So the sample data are actually taken per hour. So okay, so another thing that is important before we go into the mathematical part is the type of hydrothermal scheduling. So one is short term hydrothermal scheduling, and another one is long term hydrothermal scheduling. In the short term case, usually it varies from 1 day to 1 week maximum. So this is your short term hydrothermal planning or scheduling. For long term, it goes from greater than 1 week up to 1 year, because as I said, we don't usually go beyond 1 year, because after 1 year actually there is cyclic variation in water levels in the hydropower plants. So for the long term scheduling, usually we have to go for from 1 week to 1 year duration, whereas for the short term hydrothermal scheduling, we generally vary from 1 day up to maximum of 1 week. So in this course, actually, we will be going for the topic of short term hydrothermal scheduling, where there is a big assumption, a difference in assumption. So one assumption will be associated here, because in general, in a day, considering you have a big reservoir, okay, big reservoir. So in a day, whatever amount of load is being supplied by the hydro units, this water level, let's say this is your water level, okay, this is your, let's say this is the dam, okay, this is the, so you have a dam, and through this dam, actually you are trying to, so this is your dam, and here you have a gate. Probably in the previous course, those who took previous course with me, they have some idea about the hydrothermal generation, sorry, hydro generation. So there is some gate which can be moved up or down. So there is an opening, okay, and this is your water, okay, this is your water. So this is the dam. This is the dam. This is the water, and you have some opening here. So when you open the gate, uh, when you pull the gate in this direction, upwards direction, so you have some opening. So the water will flow due to the gravity. And of course, there are some components like penstock and inlet valve, and ultimately through the penstock and all those things, it will ultimately go to, let's say, another channel, another control valve. And again, by closing and opening this control valve, you can control the flow of water through the turbine blades. Let's say this is your turbine blades, and from here it will actually go to your generating station. So this is your let's say the generating station. This is the turbine blade. So that the turbine blade will rotate with the help of the water flow through the penstock. So this is your penstock. This is of course a very short view of the hydropower plant. And once the turbine starts to rotate, and the unused water actually will go out in this direction. And this is your generator, let's say. So generator, you step up, you use the transformer, three-phase transformer, and you transmit the power. So this is, in short, your structure of hydropower generation. So what I was saying is the height, this is the head basically. Okay, this is the head, water height of the water level, available height of the water level in your reservoir. So this is the head, and this head in a day, basically whatever change in the head level that will occur is pretty much negligible. Okay. So with this assumption, considering the reservoir is very, very large, so in a day, actually whatever change will happen in this H, whatever del H will happen in a day is of course pretty much negligible. So the del H is considered to be negligible here. There will be some change, of course, in a day, because there will be some water being used by the hydropower generating system. So there will be some del H, but that is negligible for this 1 day to 1 week duration. That is for the short-term hydrothermal scheduling. So what we will do, we will consider that for a single day, my head height is constant. That is, the head height is constant. And in other words, that means the amount of water that is available for generation, of course, with the help of the hydro system, is the amount of water available for generation is constant. So this is the main assumption that lies with this short-term hydrothermal scheduling. Okay. So with this assumption, so let's proceed on and try to formulate the optimization problem mathematically. So let's take the eraser, and now we will be switching over to the textbook. Okay, with this small intro, now we are in a position to understand, we are in a better position, of course, to understand the mathematical formulation which are associated with the theory. Okay, so let's go there. Okay. So this is article 4.6 from the textbook, that is of optimization of power system operation by Jizong Zhu. So as I mentioned, that our main target would be the short-term hydrothermal scheduling. Okay, and the duration is from 1 day to 1 week. And the time sampling that we will consider during a day or a week will be based on an hour by hour scheduling. So we'll be not taking like what is going to happen within an hour. Okay, so we'll be jumping from 1 hour to the next hour, considering that within that hour everything will remain constant to its previous value. So our target again in the hydrothermal scheduling is that we will be using some hydropower. Also, we will be using some thermal power. to supply a common load, and our target would be to achieve the minimum production cost, or in other words, the minimum fuel consumption. For how long? For the given time period. So be it 1 day or 1 week or anything in between, because it is short-term hydro scheduling. So now let's start the formulation. So we first let that PT, it is the T stands here for the thermal power output from the thermal unit or thermal power plant. F of PT, it is the associated cost function, or in other words, we can also say it is the input output characteristics, where the input is in cost, fuel cost, input is translated into the fuel cost, and the output is basically in megawatt or kilowatt generation. So this is your power output, this is your cost function. So we have one thermal plant, and we have a hydro plant where hydro output is represented by PH, H for hydro. And remember, in the ELD case, I repeat, we are only dealing with the real power. Okay, there is no reactive power cases, all are real powers. WPH is again some form of input output characteristics of the hydroelectric plant. So you have PT, F of PT, PH, and W of PH. W stands for water or hydro. So the hydrothermal system economic dispatch or economic load dispatch problem is expressed as, our target is to minimize F, all the summation of F. So if you have more than one units, then you will be using the summation. Okay. So the summation of all the cost, our target is to combine all the cost and minimize the total cost. So F summation is basically the total cost, total fuel cost, or the total running cost, whatever. And because we are introducing the hydro units and our duration may vary now, okay, duration may be from 1 day to 1 week. So we have to mention the duration like in the form of integral. Okay. So it is 0 to T, T is the total time. So if it is 1 day, so T will become 24, because we are discretizing the total time in the form of 1 hour, okay, the sample of 1 hour. So it will be 0 to 24. If it is 1 week, accordingly, you have to multiply it by 7. So that number of hours will be the value of capital T. And that has to be integrated for all the F, where now we have PT, where PT is now can be treated as a function of time, because we are integrating the whole thing as a function of time. So this is the explanation of 4.65. Such that, so this is our objective function. This is the main objective function. So this is our objective, such that now we start the constraints. So the first constraint is basically we have to satisfy the demand. So the demand at time T, let's say hour number 1, hour number 2, hour number 3, up to hour number 24, if it is 1 day. So per hour, your demand might vary, and accordingly your generation from hydro and generation from thermal should also vary. So now the pH, which is the hydro output, will be a function of time. Thermal output will be a function of time, as well as the demand will be a function of time. So your total generation is this. Now you have some hydro contribution, you have some thermal contribution, minus the demand. So basically this is nothing but P summation of P gen is P demand, where P gen will comprise of thermal and hydro. So then what they have done, they have taken the P demand to the left hand side, and that makes the right hand side equals to 0. Pretty simple. So that is 4.66. Okay. So next, so this is the equality constraint, of course. Next, we have some other constraints. So the next constraints that we have is basically, as I said, associated with the hydro unit. And in the hydro unit, you have equation 4.67 that the total water available, W sum. This is the water available throughout your duration under consideration. So let's say your duration is 1 day. So W sum will give you basically the amount of water available during this time. And as per our assumption, for short range or short term hydro scheduling, these value will remain constant for that specific period of time throughout your optimization period. And then, so that means your power output, your generation from the hydro or the water that you can use throughout this duration, the water that you can use throughout this duration for generating some output. So this can be translated as this: the water that you would like to use throughout this duration from 0 to t integrated over dt. Now this W will of course give you some pHT. So you can use the water for generating some pH, that is the hydropower, throughout this period from 0 to t, but that has to be exactly balanced by the water available to you. So that means you cannot go beyond that. Okay, so whatever amount of water is available for generation, you can use that water, and they are exactly same. You cannot go beyond that. So that is the next equality constraint regarding the hydro head or the reservoir water availability. Now for the ease of calculation, what we do, instead of this continuous form of integral, what we do, we simply transform this integral into discretized form. So what we get, instead of writing from t, we simply take discrete samples. Instead of t, what we do, we take some indexing, small k from 1 up to s. So we simply discretizing the t into s time stages, where you have k equal 1 up to s, and delta tk is your sample size. So if this is your total t, so what you are doing, k equal to 1 up 2 3 4 5 up to s, and this is your delta tk. Okay, so after discretizing, as we know that the integrals, the continuous integrals could easily be written in terms of the summation form that we are going to do next. So for any time stage, remember, this is for any time stage t. 4.66 is true for any time stage. If we want to specify this equation for a certain time stage from 0 to t, certain time stage, that means for any k, if we want to specify the same equation, so that will become something like this. So that will become now pH of k plus pt of k minus pd of k. That means p hydro at kth instant plus p thermal at kth instant, summation of these two minus the demand at the kth instant should be equals to 0, where k is equal to 1 up to the total number of instants under consideration. This is 4.66 transform into 4.69. Similarly, 4.67, which is another integral. The first part is integral, so that will be transformed into 4.70 like this. So instead of the integral, what we do, we simply replace the 0 to t integral by the summation sign, and at the end we have this del tk. So we have k equal to 1 to s summation w pH of k. So pH is not written as a function of time at any time, rather it is for some specific time instant k. Okay, w at pH k multiplied by del tk minus the total water available, w summation, equals to k equals to, so what we have is w at pH k is simply we are denoting it by wk. And del tk minus w summation is equals to 0. So this is your second equality constraint. So we have two equality constraints till now, besides the objective function. So now the objective function itself, 4.65, you can change it. It can be changed as f sum. So remember the objective function itself, 4.65, this was the original objective function. This was also in continuous domain. So if we discretize it, simply it will become f summation, remove the integral, just introduce this summation at the beginning, and at the end multiply with del tk, like all this 4.70 whatever we did here. So then it will become function of ptk. What did we have here? This was pt of any time t. Now it has become ptk at a certain instant k, then del tk, and again as we did here, wk was simply w of phk. So here also fk is simply f of ptk. So we remove the function term and simply we represent this function of ptk by simpler term f sub k. This is 4.71. So now the all of our objective function as well as the equality constraints are transformed into discretized form. So we are in a position to formulate our Lagrangian. Remember, we are not considering the inequality constraints. That means the generation limits, upper limit and lower limits, are not taken into consideration for simplicity for the time being. So the Lagrangian function is written as, what we have to do, simply the Lagrangian function is as you know, you have L. So you first take the objective function itself. So this is your objective function, main objective. Then what you do, you take the equality constraint, let's say, where you have the generation equals to demand, and you can go in both direction, like as we did earlier for ELD all thermal cases. What we did, we took it like, if you remember, it was like P demand minus summation of I equals 1 to n PGI. Then we multiplied it with lambda with a plus sign while we formulated the Lagrangian. In this case, what they are doing the opposite, but you can also go in this direction, no problem. So they are keeping the generation term first, and then they are subtracting the demand, and they are putting a minus sign there. You can reverse these two, and you can put a plus sign here, like this, plus sign there. Okay, so no problem. The result will be the same. So now you have discretized form. So for each instance, you have to satisfy PHK plus PTK minus PDK. You have to get the balance between all these three. So your lambda will be now time dependent. Okay, so the incremental rate, or the lambda, the Lagrange multiplier, will no more be a constant, rather it will be a function of a time instance. Okay, so from each time instance to another time, from each hour, from 1 hour to the next, your lambda might vary, because now you are formulating your Lagrangian for each time instance. So it is lambda k, not simply lambda. And finally you have the del tk. Okay, so then we have plus gamma. We have plus gamma, and this will take care of the second inequality constraint. Second inequality constraint here. So simply you multiply by gamma, and then you take wk del tk minus w summation, and this total thing will be your Lagrangian L. Okay, so now we are in a position to get the necessary condition. So what is the necessary condition? The necessary condition is quite simple. It simply says that you have to take the Lagrangian, and you have to take the partial derivative with respect to all of your decision variables and make them equals to 0, and try to solve the system equations to get the values of the unknowns. So what are the unknowns? We have PHK, one family of unknowns. So it's already there. PHK, that is hydro generation for each instance. This is the unknown. Thermal generation for each instance. This is one unknown, another unknown. Okay. So we have PHK, unknown, set of unknowns. PTK, another set of unknowns. Then lambda K, this is another, these are another set of unknown, and gamma, this is the unknown. So we have to take the partial derivative with respect to all these decision variables: the hydro unit generation, the thermal unit generation, the lambda, that is the Lagrange multiplier at the kth instance, and the gamma. And when you take this partial derivative, you can go through this very easily. This is quite simple. So you have to take the PHK wherever you have the PHK. So here you have the PHK, lambda K, PHK. So, and then the del TK. So you take the del TK, lambda K. Then you have here, you don't have any PHK. Remember, FK is simply function of PTK, okay? The thermal. There is no relation between FK, that is the fuel cost, and the hydro unit. So when you take the partial derivative of the Lagrangian, for the Lagrangian L with respect to PHK, you don't have any appearance of FK here. What else you have? You have the gamma. WK, interestingly, WK is a function of PHK. Remember, WK is a function of PHK. So you have to calculate dWk over dPHK, and then you have the multiplied del TK. And that should be equals to 0. And that should be satisfied for all the instances of K from 1 up to S. Then you take the partial derivative with respect to TK, PTK. Now FK is a function of PTK, so you have to take it. So dFK by dPTK multiplied by del TK, minus you have the PTK here, so it is minus lambda K and del TK, and there you don't have any appearance of PTK, so this will be ignored, and that is equals to 0. Then you have lambda K di L by di lambda K and di L by di lambda K, all the things that is available here. PHK plus PTK minus PTK multiplied by del TK will come here, and that is equals to 0. And the last one is di L by di gamma, and you take out gamma, and whatever is remaining, you simply take it and make it equals to 0. So these are the equations. And if we now follow closely from equations 4.73 and 7.4, what do you get? You can see that you have del TK here and there, here and there. So on the right hand side you have 0, so you can simply ignore basically del TK because it is non-zero. So you can divide both sides by del TK, and you can get rid of that from these two equations. So simply you have dFK by dPTK. You take lambda K to the other side. You take lambda K to the other side. So what you have is simply dFK by dPTK is equals to gamma dWk by dPHK. And both of these will be equal to lambda K. So lambda K would be taken to this side, lambda K would be taken to this side, del TK will be cancelled. So you can see that this expression will become equals to lambda K, as well as this expression will become equals to lambda K. So both of them equals to lambda K. However, this is associated with the thermal units, the cost, fuel cost at kth instant, associated with the thermal unit at the kth instant, thermal output at the kth instant, equals to gamma, some coefficient, multiplied by dWk, that is the water available at the kth instant, divided by PHK. This is the power from the hydro, power output from the hydro units at the kth instant. And this should be true for all the instances from K equal to 1 up to S. And both of them equals to lambda K. So now if we take the time stage very short, of course, as I said, the time stage in general is taken as 1 hour, okay, for a day. So then you can even get rid of the K and you can generalize this as this. That means if the value of del Tk is very small, you can even generalize this. The total time is, even if you can consider the total time stage is very short. Okay, then let's say 1 hour. Okay, 1 hour only. So you can get rid of K and you can drop out the K and you can simply write this relationship. So now equation 4.78, that is this. For the hydrothermal system, we get some relationship for equal incremental principle. Okay, this says, remember, for the all thermal units, we had something like this: dF over dPt equals to lambda. This was the case for all thermal units. You can check back anytime. For the hydrothermal coordination, you have some additional terminologies like this. Okay, both of these two are actually equal to the same lambda. So the equal incremental principle means for the hydrothermal system, economic dispatch, what you can do basically using this relationship, you can find some physical meaning of gamma. Let's see how we can get that. What is the physical meaning or physical significance of gamma? So for finding out that, what we can do, we can replace this d by the small increment del. So what do we have is del f by del p. So what we are trying to do is simply we're trying to replace this df by dpt is simply del f by some del p. So if that is done, then we can say, well, the del f would be simply df over dpt into del p. Okay, similar thing could be done for the hydro case. So if we do the similar thing for the hydro case, we get equation 4.80. So this is something like saying you have del w over, this is w not omega, del w over del p is assumed as dw over dph. So we are replacing d by some small del incremental variable, and then that del omega del w can be written as this. So using equation 4.79 and 80, we can get this relationship quite easily. Okay, so what does this say? This says that you have some incremental change in water consumption and you have some incremental change in the fuel cost. Remember, F here is the fuel cost. So this gamma is basically a coefficient which translates the water consumption into equivalent fuel consumption for hydro units. This is the explanation of this gamma. Quite interesting. Because we said that there is no fuel cost associated with the hydro units. So, but there is some water consumption available with the hydro units. So this gamma basically helps to translate the water consumption into some corresponding fuel consumption. Okay. So this is the explanation, physical significance of gamma here. So in this manner, we can find out what is our gamma. Okay. And in other words, we can say, we can read out this, that the water consumption of a hydro unit, if you multiply that by gamma, that means if you do like this, water consumption of a hydro unit multiplied by gamma is equivalent to the fuel consumption of thermal unit. I mean, if you want to relate the thermal consumption and the water consumption, you have to take help of this gamma. Okay. And in this manner, we can say that, well, the hydro unit could be treated as the equivalent to a thermal unit. So you cannot directly say del W is del F. To say this, you have to take help of this gamma. When you introduce this gamma, if you multiply it with del W, then it is identical to saying that, well, instead of a hydro unit, you can consider it to be a thermal unit. So this is the significance of gamma. So with all this, we are now in a position to have a look into the next topic. Although in the book they are discussing an algorithm, this algorithm I will discuss inshallah in the next class. That probably will be the last class before mid. So before I go to this algorithm, I will be discussing actually the algorithm which will be a little different than this, not exactly as this. So I will just skip it for the time being, as well as the example, because the algorithm that I will discuss inshallah, I will use that algorithm to solve this example 4.7. It is similar to the algorithm that is mentioned in the book, but a little bit more explanatory, okay, than this. So now let's jump into the next topic that is of course associated with the hydrothermal case, but now we will be introducing the network losses. So when we introduce the network losses, then our equality constraint will be updated, okay, as we all know. But there is a little bit more complexity added here in this book. Instead of considering one hydro plant and one thermal plant, they are considering m number of hydro plants and n number of thermal plants. So in total, you have m plus n number of generating units. The system load is again given in the time period. The time period could be from, because we are considering the short term hydrothermal scheduling. So of course, the time duration would span from 1 day up to 1 week, minimum and maximum limits for the topic under discussion. Now, if we consider that, well, we have m hydro plants, so each of the hydro plants may behave differently from one another. So I'm considering that, let's say the jth hydro plant is consuming or can consume W sum J, this amount of water during the time under consideration, and this will remain constant throughout the duration. The hydrothermal system, economic dispatch with network loss, then we can express it. Remember, n number of thermal plants. So in the objective function, you only bring the thermal units. Remember, there is no hydro units cost, fuel cost. So you see I equals 1 up to n, and the remaining part is as before. Simply the additive part, what we add here is Fi and Pti, I here for the index for the thermal units, specific thermal units. Okay. This is because we are considering more than one thermal units here, and also more than one hydro units as well. So this is the objective, and then you have the constraints, equality constraints again. So the constraint is you have the j equals 1 to m summation of pH j as a function of time. So this is the hydro unit. All the hydro units, you are adding them up for j number of units, plus I equals 1 to n. You are adding up the thermal outputs for n number of units, minus PL, this is the load at instant t, minus P demand. Oh, sorry, PL is the loss. Okay, this is what we are introducing here. The network loss is PL at tth instance minus P total demand at tth instance equals to 0. So your generation PH and PT should be equal to the loss, transmission loss, plus the demand. And the last one, 4.85, is like the previous one. This is associated with the water head available. Okay. Now the additional indexing J will be there. So similar to the previous section, that is 4.6.1, without network loss, the hydrothermal scheduling, what we do again, we take the total time period T and we sample it with the help of del T. Kth instant, K is the index from 1 up to S. So we discretize our objective function 4.83 as before. So we have F summation. Already we have this discrete term summation of I equals 1 up to N for all the thermal units. And this integral we are going to replace by this summation K equal to 1 up to S. And at the end, instead of dt, we are going to use del Tk, Fi of K, Pt I of K. This is 4.87. Then the equality constraints, again, we don't have actually any integral here in 4.84. So basically 4.84 is exactly the same as 4.88. Okay, so a little different because this function of t is actually replaced by the kth instance. Okay, there's a difference. So the function of t is actually replaced by the kth instant, kth instance, kth instance, kth instance, all everywhere throughout this expression. And k is from 1 up to s. 4.89, this is basically associated with 4.85. So we remove the integral from 0 to t dt, and we know how to do this. So you have to start with the summation k equal 1 up to s. Now it would become a function of the kth instance, then phj kth instance multiplied by del tk instead of dt minus w sum j, that is equals to 0, and that is for j equals to 1 up to m number of hydro units. The Lagrange function, you can formulate it. You have the fitness function 4.87, that is objective function, minus the lambda k into this whole thing into del tk, then plus. Now remember, you have more than one hydro units, so the conversion from del w to del f might be different or could be different from one hydro unit to another hydro unit. So you have to take multiple gamma here for m number of hydro units. Other than that, it is this exactly same as the previous topic that we discussed today. So now we have the Lagrangian. You take the necessary condition. So you have the unknowns ptik, phik, lambda k, and gamma j. So again, you take the di L over di H J K. I think you can do it on your own. So a little bit of variation from the previous one, because now we are considering the PLK. And remember the PLK. So this is one thing that I should mention here. So PLK, remember, because this is the network loss. That means when your power is coming from the thermal units, this is, let's say, thermal, and this is, let's say, hydro, and this is your transmission network. Let's say this is your transmission network. In short, this is the bus, and this is the load. So throughout this transmission network, when you are considering the loss, your contribution for the loss is coming from the thermal unit as well as from the hydro units, remember. So the di PLK is or will be actually a function of the PHJ at the kth instant as well as the di PT and then K. Okay, di PT IK, I mean di PT IK and di PHJK. So when you take the di L with respect to di PHJK, your di PLK here has to be differentiated, partially differentiated with respect to the di PHJK. And you have to do the same for di L over di PTIK in the next line that will come. So this is one additional thing that we have to take into consideration. So here the J, the value index J will be from 1 up to M, that is the total number of hydro units, and K, it will be from the total number of time slots, time samples. Then your next unknown is diptik. So dipti, the fik is a function of ptik. So you take dfik by dptik into del tk minus lambda k 1 minus, you see diplk again taken, because diplk will be a function of both phjk as well as ptik. And then del tk, here I is for all the thermal units, so 1 up to n, k is for all the instances 1 up to s. Then you have di L by di lambda k. So simply this whole thing will come, and that will be equated to 0. Di L over di gamma j. So now this whole thing will come, and that would be equals to 0. So you have got 4.91, 92, 93, 94. From 91 and 92, like before, we can simplify, okay, and we can show that, well, that, so now we have some additional term. Previously we didn't have this, but what we can do from 4.91 and 92, we can again get rid of this del tk quite easily. So let's get rid of this. We can take this lambda to the other side. We can take this lambda to the other side, to the right side. So we'll be having something like this. So what we'll have, that is written in summary here. So we'll be having, let's say, dfik by dptik. This is here. And what we can do, we can keep lambda k. For further simplification, we can keep lambda k here. And this whole thing, we can take to the other side. And we can multiply it with this by simply 1 upon the whole thing here. 1 upon the whole thing here. So this is what is done here. This is what is actually done here. So dfik by dptik multiplied by 1 upon 1 minus the whole thing here equals to gamma j. So the gamma j dwj by dphjk, and again you can take the whole thing to this side, and you can multiply it 1 upon the whole thing, whatever you have here. Okay, that is 1 upon 1 minus diplk by diphjk, and both of these will be equal to lambda k. Okay, after you bring this one here and this one there, on the right hand side you will be left with lambda k. So on the right hand side you will be left with only lambda k, and here k will be from 1 up to s. Again I will be from 1 up to n, and j will be from 1 up to m. So this is the incremental principle, incremental cost principle, considering network losses. Okay, so now we can say, well, if this is equal to lambda and this is equal to lambda, so we can get rid of lambda and we can say, well, this is equals to this. Okay, so this is for this relationship will hold true for the case where you have considered the network losses. So equation 9.5 is true for any time stage. Here you had the kth time instance, so it should be true for all the time instances starting from 1 up to s. So for any time instance, you simply get rid of k, and you can simply write it like this. And equation 4.96 is the coordination equation of hydrothermal system, economic dispatch, considering network losses. So when you didn't take network losses into consideration, you actually didn't have this, just in the previous topic that I discussed today. When you have the network losses introduced, you have these additional terms. That's it. Okay, so I hope I shouldn't go beyond this for the time being. So in the next class, inshallah, I will be discussing the associated math problem, the algorithm, and then I will solve a problem that is given in the book. Okay, so please go through this lecture before you come on Friday, next Friday. If you have any query, we can discuss it first like other classes, and then we will proceed with the problem solving session. Okay, so thank you very much. Assalamu alaikum.